Hi, my name is Flora Nguyen, and this is my lab report video for Lab 3, Black Hole in Orbits. This lab is divided into two parts. For the first part, the purpose is to observe the motion of a star orbiting around a black hole on a computational model and determine the mass of the black hole. For the second part, we're going to find the initial velocity of a spaceship for it to travel a safe orbit around the planet and the moon without crashing into either one. The fundamental principles covered by this lab are Newton's second law, or the momentum principle. The momentum principle states that the net force acting on an object is equal to the rate of change of its momentum over time. And in this lab, the only force impacting the star is the gravitational force from the black hole, and that's the total net force. The net force is also split into two components, including parallel and perpendicular components. The parallel component only changes the star speed, and the perpendicular component changes the star's direction. And we also have the Newton's law of universal gravitation, which states that every object in the universe attracts every other object with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. We will use that to solve for the mass of the black hole, and from the momentum principle we can derive the velocity update formula. Final velocity equals to initial velocity plus net force over mass times change in time. And we also have position update formula, which is final position equals to initial position plus average velocity times the change in time. For a brief overview of our results, here's a demonstration on close grip and the mass values calculated. The orange arrow is the net force, the cyan represents the perpendicular component, and the magenta color arrow represents the parallel component. And later for part 1, we would look at these masses values to get the average mass of the black hole. And for the second part, here's the trajectory generated that shows the motion of the spaceship and the moon, and here the initial conditions that I selected allows the spaceship to orbit the planet without crashing into either body. For part 1, the system is a star and the surroundings include everything else that includes the black hole as well. And for this part, the procedure is very simple. We use the starter code and plug in necessary information to compute a computational trajectory in CloseScript using my Georgia Tech email as a randomization seed. For the initial conditions, I plugged in the mass of the star and delta t as given from the lab instruction. Then I put in the formulas for initial and final momentum, which is then used to calculate net force using the formula delta p over delta t. We then put in the formula to calculate the parallel and perpendicular component for net force, and finally the mass of the black hole is calculated using Newton's law of universal gravitation. And here is a simulation. We can see that as the star moves closer to the black hole, the arrow gets bigger because the gravitational pull between the star and the black hole increases. And from these mass values calculated from CloseScript, we can calculate the average mass of the black hole, which is equal to 1.57 times 10 to the 34 kilograms. Moving on to part 2, the system here is a spaceship while the surroundings include the moon and the planet. For the procedure, we modified the starter code to calculate the gravitational forces and solve for a initial velocity that works. Now looking at the code, we are mainly using the formula for Newton's law of universal gravitation. The code logic stays exactly the same for each force calculation, and the only thing we're changing in this case is the mass, and that depends on which two objects we're looking at. I also plug in the position and velocity update formula, which the code uses to calculate the new velocity of the moon and the spaceship and update their positions at every individual time step. From the actual trajectory, my chosen initial velocity was successful in allowing the spaceship to successfully escape the moon's gravitational pull and enters a safe orbit around the planet without crashing into the objects. And the potential sources of errors throughout this lab include rounding errors, because as the code updates positions over thousands of simulated hours, there could be tiny rounding math errors that can build up and cause the path to slightly drift. And another error comes from ignoring minor forces. In our code, we simplify the system by only calculating gravity between major objects, so we are also ignoring potential smaller forces that can affect the simulation. And for the first discussion question, the answer is that the rate of change of momentum can be calculated by observing the change in position and velocity over time, but net force from the black hole is not something that is measurable and can only be inferred from the change of momentum. And for the second question, the code would need to calculate the gravitational force between every single pair of objects using the law of universal gravitation, and these forces would not be equal because the dominant force would come from the black hole. And that concludes my lab 3, and thank you for watching.